Today I want to talk about autonomous agent training, nurture versus nature. I kind of go through several examples that we did recently, dancing the fine line between what data we use, what environments we use versus how we construct the agents. So let's look at the video here first. So if we want really robots to be out there in wild, working in unstructured environments around people, like this robot needs to go from one point to the sink over there. It needs to deal with whatever kind of happens. So now this path is blocked. It needs to go around and find its way around people and so on. So not only it needs to perform tasks well, but it really needs to adapt to many different changes in the environment as they occur. So that this is what we call generalization. This was not staged. Custodian appeared here and robot needed to deal with that. So it's important for the models that we have that are both performing well and generalize. And this is reinforcement learning robot that is fully trained in simulation and then put on the robot to adapt, to run on. So generally when training agents, we have many different levels, but two of them are data. That's things and environments that we choose to train the agents in. So either producing the data or simple simulators or more complex simulators and so on. And to a certain extent, this is the nurture of how we nurture the agent. What is that we're kind of providing it to be able to learn well. On the other hand, a whole set of different decisions is around what neural network to use, what loss function to use, things that are basically structure of the agents and thinking about that as a nature of the agent, because it does not change during the training and so on is building. And as we're building these models, we change the data a little bit, we can change the representation and so on, and it's really not clear which one is more important for what is their fundamental relationship, and so on. So I'm going to give several examples that kind of tries to tease out this line, and it's very blurry and it's very connected, and it's more to open the conversation in this area to help us understand where we stand. So for examples that we're going, this is really a spectrum. So maybe things on the left side are more data oriented and things on the right side are more representation oriented, but it's really blurry line. So first example is web navigation, where the goal of the agent is to have a single agent that can navigate and complete any form filling tasks on the web, such as, I don't know, login or password change or complete a purchase and whatnot. The second task, or the second topic that we're going to discuss is the mobile, or not the mobile, manipulation task. It is again compositional task, complex task, when we're kind of learning to do sequence of different manipulation tasks, such as stacking and routing and so on. Third example is the visual language navigation, where agent is supposed to provide human usable navigation instructions. And the fourth one is on the game design, pure, can we learn better neural network architectures and what they give us in the space. Lost the cursor. Okay. So the first work is on the autonomous web navigation, which I mentioned already. It is really a mobile manipulation task, if you think of it. Consider completing a checkout process on a, say, Walmart website, or doing a password change and so on. We go through several pages through that workflow. Each page can be considered as a room. In each room, we do some manipulation on that. We enter our first name, we enter the password, then we go find a door, which is really a submit button, right, which kind of gets us to the next room to complete another manipulation task and so on. So without the embodiments, are very similar to robotics. And we want to have a single agent that can complete any task. So why is this reasonable expectation? Well, for one thing, we can do it. We don't train first every time we see a website or ads change or pictures change and so on. We don't retrain from the beginning. We can do it. So there is a proof of concept in humans. However, the existing methods, real websites are difficult and prohibitive to use for training because, well, they're expensive and there is a safety component to that. And they're large compared to the previous existing benchmark that had only about 100 DOM elements. The commercial flight booking websites have the order of 30,000 DOM elements. So, and then the models that existed were able to solve a single domain with millions of samples and do not generalize beyond. We want to go for the generalization. So what we did is we created what we call G-miniweb. It's a generative miniweb environment, and it is capable of generating websites. So it starts with a palette of skills or the widgets, if you want. I don't know, enter the field, the drop down, and all the 9 yards. And it has the placeholders for end pages, and then you can create at will, basically place the elements on the pages and so on. So we can generate realistically large looking websites that we can do. Okay, fine. How do we train then the agent? It is a very long horizon task. So we can't just go and do here is the website reinforcement learning, go and do it, because the reward is very sparse and it's not scalable. So to address that, we actually trained 2 agents. One which we called design agent. It is supposed to provide the training environment for agents to train on. And it is supposed to create just the right challenge for the level. It's an LSTM. It's an LSTM that decides how many pages are going to be in that website that it creates. It decides how many elements are going to be per the page and which elements are going to be. So you can create very simple and you can create very complex websites. So LSTM generates a proposed website. So then we train an agent population. In this case, these are reinforcement learning agents that are trained with a success reward. And once they succeed or complete the training, several steps and so on, we observe how well they did and send back to the design LSTM regret or basically range in the performance of the agents and how well the best performance agent is doing. And this is the signal for the LSTM to say, hey, this was very difficult challenge. So let's tone that down and let's go easier. That's kind of encoded for the loss. There is a two-level loss. Or if everybody was solving the problem, that means the challenge was too easy. So it should increase the difficulty of the design. And then the second, the range tells the LSTM, this is the second part of the loss, is if there is a mixed performance, this means this was a good challenge, right? Because some agents are able, some are not, and so on, which is very different that everybody succeeding or everybody not succeeding. So that kind of gives the signal as what elements to put on a website. For example, if the website that LSTM produced contains only images and nobody can complete the task, that's a signal that it needs to change and needs to provide some elements that enable the task. So we basically have 2 agents co-training each other while the design is being trained to produce the appropriate level of difficulty training, and then training agents are training to complete the task. And then we go and evaluate the agent on never before seen website and observe the performance. One thing that's very interesting here, that this method is agnostic on how we train the population of agents. In this case, we're using reinforcement learning, can be imitation learning, can be on humans, right? Doesn't matter. The only thing that we need to be able is to observe how well they're doing. On the other hand, the training population is completely oblivious to where these environments are coming from. In this case, this is learned curriculum, but for all they know, they're just being presented the data to train. And one key factor here is compared to the prior work that we've done that does not generalize to more websites, the only difference is these environments that are being produced by the design. So if we just train on a single website, we're not going to get generalization. Once we have diversity of the environments, we start seeing generalization in the performance. So in the results, we first see that the environments become more complex as the training continues, which is kind of expected. As I mentioned, we see that the agent generalized on thin environments. And two other methods here that we compare, blue line is the proposed method. The other two methods are two different ways to do a curriculum, manual curriculum and curriculum without the tool loss part. Just uses the variation of, it does not use the difficulty component of the loss. And then we see that over the training, the distribution of the primitives shifts towards more task relevant things. So that's very interesting. And briefly, just to kind of estimate how well this works on real websites, we took 3,500 primitives scraped from the web, which is basically different ways to do input field and so on, which induces the task space of 10 to the 31. So pretty large task space. And most of because it's a real data, it's unbalanced. Most of them fall under username and passwords, so kind of mixing with the login field. And their performance on the benchmark is okay. I mean, this creates 62% on where there was data and representation, does worse where there was no data representative. However, when we go and take these same primitives and the agent that we train and put it and test it in the environments that we did, we get success rate about 90%. That's the green line, which basically tells us that the benchmark that we put there is realistic, it's difficult enough, and it's worth using for studying the complex or compositional tasks. So on the web navigation here, we saw that curriculum, which basically just provides the new training data or the appropriate training data, I should say, the appropriate nurture to the agents, really improves generalization greatly. So the second is about manipulation tasks. This was actually a paper just presented here at ICRA a couple of days ago. We proposed the multi-ravens benchmark, and it is a compositional, again, benchmark, which means that we have, in this case, 4 different types of basic skill: placing, chaining, ranking, and stacking. That each of these stacking tasks can be, okay, we need to stack either 1 or 2 or so on, or different ways to route the cable between the pegs and so on. And then the multitask example that we want the robot to learn to do is the combination. So we need first to do placing and then chaining and then routing. So here's the initial configuration, and here is on the right side the target configuration. And this is inspired by assembly tasks, and being able to, from basic skills that we have, compose into more complex tasks. So to train this agent, previously, goal condition transporter networks do picking and placing. Basically, they decide what is the start and the goal position that the manipulator should pick and where it should place. And it learns from the current observation, which is a column of images that basically do top-down projection. However, when it works well for the single task skills, but when it gets to this compositional sequence condition transformer, things start to break down. So what we propose is a new module, neural module, that decides the next goal to provide to the goal condition network. So it takes, again, the current state as an observation and gets a sequence of demonstration. And we're really looking at very small number of demonstrations. And out of this demonstration sequence, it produces the next step goal. So this would be things like, okay, now if I need to do picking and placing, the next step goal should be, let's do picking first. So get that configuration and send that to the goal conditioned network. So turns out that's not quite enough, because out of the sequence, then the next goal sequence, for training, we need to decide which samples, which time steps in the long sequence we should sample. So we also introduced the weighted sampling at the task level and at the step level. And here are the different weighting samples. So basically, once it's presented in long sequence, it samples steps here to give to the next step agent. So what are the results? To collect the demonstrations, we use a stochastic policy. So it's not perfect policy. It's just presented with a random initial configuration and goal configuration and tries to solve the tasks and so on. So they're not perfect demonstrations. They're cheap demonstrations that can be automated. And here are the examples with just using 100 demonstrations. The red line is the goal condition transporter network. So without the next sequence goal with the different weighting samples. And the blue line are the sequence conditioned transporter networks that are able to take the full demonstration. And we see that it outperforms in the complex tasks, the goal condition, which means that this next step module enables generalization to these compositional tasks. And in effect, it's kind of similar to the web navigation that we introduced a model that filters out the world and gives to the goal transition network the right goal. So again, this is again combination. We added a representation, we added a module that produces the right data for the other agent to do. The third example, and I'll go fast because I know we're running time, is in the domain of visual and language navigation. And one thing that we want to do here is one major step in human-robot interaction is to be able to communicate with robots with really natural language. So in this case, we want to learn a model that can produce human readable and executable navigation instructions in this room-to-room data set, so going between the rooms and so on. And prior work in this space, first had the humans annotate or create the descriptions for the instructions without actually following the path. And that had mixed results because it was difficult for humans to visualize what can be seen. And then the models that were kind of coming out of that were creating lots of landmarks that were not visible or not appropriate and so on. So finding the relevant landmarks to give to humans that follow instruction is a key. What we mean by relevant means that they can be seen, right, at their appropriate level, and so on. So this is about finding the relevant landmarks. And this is paper that's going to appear at CVPR this summer. So we take a small number of annotated landmarks and go in 3 phases: landmark extraction, landmark detection, and instruction generation. So we asked for a small number of annotators, I think it was 100 to 200, to speak while traversing the path. So we're training the agent. Here is an example here on the right side that they produced an instruction along with a trajectory that tells them that when there is a connection at the timing of each word and the image that was seen by the annotator at the time. So you're standing inside of the washroom, that's time step 1, turn right and exit the washroom, and so on. And from there, we can extract the keywords or the landmark keywords in these instructions and associate them with the images that were seen at the same time. Now, caveat here is that there are no guarantees that humans had seen these, that they were visible in that particular moment. Maybe it's something that they remember, so it's kind of weak supervision setting, but regardless, it's enough. So we extract these and then we train a model on the left side here that says, okay, here are the images that are seen, here are the extracted keywords. What is the probability that this keyword is applicable on the current image using the attention? So that's our landmark extraction, and we extract about 900,000 landmarks. So then once we have the images or the trajectory that somebody had followed that we want to describe, which is a series of images, we can go through this image and extract relevant landmarks. So in this case, this can be, well, here's the washroom or the bathroom and so on. And we can go from there. And then the third step is the instruction generation. In this case, now that we have the trajectory, we can describe in kind of very templatic language that trajectory, things like, I don't know, ahead is the washroom, go hard right towards the door, and so on. And the landmarks are put as an images. And that goes into fine-tuned multilingual large language model that can then produce English, Hindu, or Telugu instructions that are human readable. And we see here is an example of, from the first slide, one instruction that it can give. If we subsample landmarks differently, cool thing about that is that it gets equivalent instruction, but differently phrased. So that's very cool. So there's a variation there for the interest. And then we verify the produced instructions on humans, how well they can follow them. And we see that on the room-to-room data set, it almost closes the gap with human-generated instructions. So the instruction generated with this model produce 71%, whereas human-generated instructions result in 75% success rate. So this is an example where we're, again, changing the data, but we're learning the appropriate data from the small number of annotated examples and helping with the instructions, with the instruction following. And then the last thing, very briefly, is question how well, if we did not change the data and just went to improve neural network architecture, what's the benefit of that? And is there a benefit? So in this case, we look at the differentiable architecture search and reinforcement learning. We use a method called DARTS that basically creates a supernet. You can provide what are the operations, and then different operations on that network create a graph, and the edges of that graph are whether operations are connected or not. And as we train the agent, the loss function adds not only performance, but differential, the way it learns the weights on the supernet, and some edges fade or some don't or strengthen. And after the training is done, then we take that supernet that was there and discretize it. So weights that are below certain threshold or edges that are below certain threshold just kind of get disconnected, and those that are strong become edges in the neural network architecture, and then we evaluate it on the target tasks. Nice thing about this is that it's generally very easy to plug in because it just added a loss term to the existing method. and there is a low computational cost compared to the neural network architecture searches. So we evaluated on ProgGen. So we evaluated on the ProgGen on the left side and on Mujako tasks on the right side. On the ProgGen, we're using Impala, which is generally state of the art. And on the right side, since Mujako and continuous actions, we use soft actor critic. And we see that many environments do benefit from learned custom tailored architectures. In some cases, we see up to 250% performance compared to the manual architecture design. And the computation time is 3 times, which is non-insignificant, but compared to some other methods that are looking at hundreds or thousands x more computation time, this is fairly reasonable. And then kind of just looking at the 2 architectures here for the game specific, we see that this is an example on, I think, the Plunder game. 2 different architectures that came in. What's interesting with the bottom one is that, for example, the convolutional layers are coming later in the network. These are interpretable graphs. They're out there. This is going to appear at the AutoML conference this summer. It's open sourced, and it's interesting to go in and look and analyze the results. So we looked at the 4 different examples in this spectrum between just changing the data in the environments to just changing the neural network architectures. That here shows that it improves the performance. It still raises a question to think about: what is the fundamental role of nature versus nurture? When should we invest in better data, better environments? When should we invest in better representation, neural network, changing the agents, and so on? And I don't think that we have good understanding on that yet. Maybe we're kind of teasing. It'll be very interesting and very helpful from the practical perspective to be able to do that. And I'm looking forward to kind of see where the community lands. Similar to that, I think a couple also questions that are tightly coupled with that is, are we going to need in the future simulation in the loop, or will data be enough? And in under what circumstances data is going to be enough? What type of data, how cheap data, and so on. And third question, again, related to that is, at what point do we start creating generalist systems? And when we do a targeted system design or application-specific design? And where is that line? Or do we do fine-tuning, have a good generalized large models like language models are doing, and then we fine-tune them and specialize them in the agent space? I think these are questions that will be very interesting to see answers develop over the next couple of years. And with that, I want to thank you, and I want to thank my collaborators, and here are the links to the 4 papers I mentioned today. Thank you.
So I think we have time for maybe one question for Aleksandra if anyone wants to ask. And while we're doing that, if Judrin and Chad want to come up, we're going to get ready for a panel discussion with all 4 of our previous speakers. And I guess if there's no questions, I have one for Aleksandra, which is for your visual-based navigation, where you were doing the landmark extraction and so on. I was wondering if you could talk about essentially how that relates to maybe some of the other environment representations that we've been talking about today. Like, you know, essentially, how does that kind of create a map of the environment? Would you argue that that is the representation? And yeah, how does that relate to things like SLAM?
So in this case, it's orthogonal to SLAM, or SLAM can use the key work. The key idea behind this work is to find the relevant landmarks, and relevant is with respect to the agent, whether that's human agent. In this case, it's a human agent, right? or can be a robot and so on, that that agent can understand and it's relevant to orient itself. So how that relates to SLAM, in a sense that SLAM can use these landmarks, and the landmarks that are related to humans, or adult humans for that matter, are different than it would be for children, right? Because they're shorter and they can't see well, or for robots that have different sensors and so on. So the idea is that the landmarks need to be tailored toward the system or the task that we're using. And this is just kind of one technique, how to have the relevant landmarks in that space. Does that answer?
Yeah, absolutely. Perfect. Thank you so much.
Thank you.
Let's have one more round of applause for Aleksandra.